All right, would you turn your books to page 643? Today we're going to talk about tessellations, and we are going to work kind of along with our symmetry we did yesterday. Objectives today for the tessellations 9-6. I can use transformations to draw tessellations. I can identify regular and semi-regular tessellations and figures that will tessellate. So we have some symmetry here, glide reflection, translation. We've done all this stuff before. We just are going to do it in a different type of manner. A pattern has translation symmetry if it can be translated along a vector so that the image coincides with the pre-image. Freeze pattern is a pattern that has translation symmetry along a line. So both of these freeze patterns down here have translation symmetry. The pattern on the right also has glide reflection symmetry. So a pattern with glide reflection symmetry coincides with its image after a glide and then a reflect. So move it over and then reflect it. A lot of these tessellations that you find here can be found in many different patterns. You find them in patterns a lot, like carpet squares or tiles in the bathroom or tiles on your floor or whatever. They just have a lot of those patterns in those for that type of stuff also. Art applications identify the symmetry in each wallpaper border pattern. So if this is our pattern here and it's the musical notes, we want to know what kind of symmetry does this have. So we're looking at that pattern. Does it look like we have reflected these at all, or does it look like mainly like we just slid one across? Well, letter A here just looks like a translation symmetry. So it is, you just moved that musical note over to the next one. So in other words, you just slid this one on top of that one on top of that one on top of that one. You just slid those on top of each other, and that's just a translation. And for the dog prints, could we slide these on top of each other? Yeah, sure could. Could we reflect them? Yeah, they're pretty symmetric. You know, if we reflect this over a certain line, we could probably get them to reflect. Or we could glide them and then reflect them. So I think we got translation and we have some glide reflection. So we could slide it over and reflect it also. Identify the symmetry in each one of these freeze patterns. This is on page 643 on the bottom there. Do these two problems, please. All right, let's take a look at these. The first one, you know, it's a pattern there, but I don't think we could reflect it anywhere. Like I don't see a reflection point where we could get that to reflect. So I think that's more going to be a translation symmetry. We're going to have to slide that whole, that whole thing down or right or up or left or whatever, and to translate it. B here looks like we have a kind of a center point that we could reflect across. We could slide it over like the first one so we could translate it. And I think we could also reflect. So this one's going to be a translation symmetry and a glide reflection symmetry. Tessellation or tiling is a repeating pattern that completely covers a plane with no gaps or overlaps. So like I said before, comes in wallpaper, lots of patterns, of course, tiles, carpets, rugs, all that kind of stuff. If you've ever seen those type of patterns, that's what tessellations are, tiling. The measure of the angles that meet at each vertex must add up to 360 degrees. So in the tessellation shown, each angle of the quadrilateral occurs once at each vertex because the angle measures of any quadrilateral add up to 360. So what they're trying to say here is this quadrilateral has 4 angles. Excuse me. And you see you have a blue, a green, a red, and a yellow. And those 4 angles should add up to 360. So when we've tiled this or drawn this tessellation, in each corner or in each vertex, we have one of each color, hence proving or giving us exactly 360 degrees. The 4 corners of that quadrilateral meet at each vertex. So we've kind of shifted them over. You can see how we've rotated them or reflected them or whatever. Got it to look different like that. The angle measures of any triangle add up to 180. This means that any triangle can be used to tessellate a plane. 6 copies of the triangle meet at each vertex as shown. So again, when the corners of the tessellations meet, they have to add up to 360. Well, the 3 angles in this triangle add up to 180. That's the triangle sum theorem. So if we create a vertex, we have to have 2 of each angle. And in doing so, we create 180 plus 180, which is 360 degrees. Copy the figure and use it to create a tessellation. So copy this figure down and we need to create a tessellation. And of course, we know that we're going to have to put each corner in there 2 times because it's a triangle. So we're going to have to add up to 360 degrees. So we're going to rotate the triangle about the midpoint of one side. So for example, we picked a spot in here, right here. And we rotated that 180 degrees. And we created our other triangle. Translate the resulting pair of triangles to make a row. So now I'm going to turn that into a row. And then I'm going to translate the row of triangles to make a tessellation. So now I'm going to translate that down to here. And then I'm going to create a row or a second row of triangles. And I make essentially a tessellation. So I copy one figure and then translate it to make rows. Another example, I'm going to rotate it about the midpoint of a side. So I'm going to pick this side and I'm going to rotate it, and I'm going to end up with this type of figure right here. And then what I'm going to do is I'm going to take that figure and I'm going to translate it down or to the right, create a row. Then I'm going to translate a row down and a row over. And another row down there. And again, remember when you get to these corners here, we got to have one vertex from each corner of that quadrilateral. This one's tough, but I think I'll just show you this one. I think I'll just go through this. Okay, first step, find a midpoint. The side they picked was the right-hand side there, and just rotated it. End up coming up with that. Then we're going to make a roll. So we just create another copy of that, or translate one copy of that to the right. And then we're going to translate that into a row. And remember here, we still have 4 or a 4-sided figure. So we still have a quadrilateral. So still at every vertex, even this one, you have all 4 angles. You have the point on the bottom, the concave one that is here, this angle here, and then the 2 little ones. A regular tessellation is formed by congruent regular polygons. A semi-regular tessellation is formed by 2 or more different regular polygons with the same number of each polygon occurring in the same order at every vertex. So regular is congruent regular polygons. Semi-regular is a couple. So this would be a regular tessellation where we have all of the same figure. All those are all equilateral triangles. This would be semi-regular, which means we have squares and equilateral triangles with 2 different types of figures. Each vertex has 2 squares and 3 triangles in this order: square, triangle, square, triangle, triangle. And what they mean by that is this right here. So square, triangle, square, triangle, triangle, in that order at that vertex. Classifying tessellations. So again, we're going to classify these as regular, semi-regular, or neither. In the first one there, we don't have regular polygons, so that one is neither. In the second one, it looks like those are equilateral triangles, so I'm going to say that is regular, since it's only triangles. They're all the same. And the next one looks like we have triangles, maybe some squares and some hexagons, and they all look generally regular. So I would probably say that one is semi-regular because it has different types of, or has 3 different shapes. So semi-regular, hexagon, squares, and a triangle. Do these, classify each of these tessellations as regular, semi-regular, or neither. Remember, regular is same. Semi-regular is a couple different shapes that are regular polygons. And then if they aren't regular polygons, it is neither. All right, let's take a look at these. So for the first one, those all look like they look pretty much like regular hexagons. So I think that would be a regular tessellation. Excuse me. Second one, we're using hexagons and triangles. But they all look like they're pretty regular. So I would say it's semi-regular. Oh, neither. I wonder if it's because of the hexagons. The hexagons must not be regular, or the triangles. So that one is neither. We're not using regular. Must be the triangle. Must be this side right here. That base of that triangle must not be the same as these two. Or else it's the bases of the hexagon are bigger than the rest. Because the next one, you can tell the difference, I guess. The next one looks like it probably does have equilateral triangles and regular hexagons. So this one I think would be semi-regular. Oh, that might be it too. The vertexes are, actually aren't the same. If you look at this one has a vertex right here where it has two triangles connected with two hexagons. And then here they have two triangles tip to tip there with the two hexagons. And this one over here, they have, the two triangles are nose to nose in every single vertex with two hexagons. So those are all nose to nose. So they are set up the same. These ones in this one here, however, are not set up. They're not all the vertexes aren't the same. That's why it's neither. Determine whether the given regular polygon can be used to form a tessellation. If so, draw the tessellation. So first thing we got to figure out is these are regular polygons, so their angles. So for example, this is an equilateral triangle, so all the angles are 60 degrees. Can we get 60 degrees to go into 360? And that's yes. So 60 degrees would go in there 6 times. So we can get those, and we see here that every vertex has 6 triangles or 6 angles of those triangles meeting. For B, we got to look at this. This is a regular pentagon and a regular triangle. So now we got to figure out what each angle is. Well, in a pentagon, there is inside a pentagon, there is 540 degrees divided by 5, which gives us 108 degrees at every angle. And a triangle is equal to 60 degrees, a regular triangle. So is there any way we can add up 180 or 108 and 60 and get 360? And I'm going to say no, that 360 is not divisible by 108 and 60. So since we can't have any solutions that we have a number of vertices from the pentagon connected to vertices with the triangle, we're going to say no. So remember, these are regular polygons. Okay, it says it right here, which means all of their angles are equal. So you have to find the sum of the interior angles. And how do we do that? Well, B is 5 minus 3 times 180. And the triangle is 180. So you divide that by 3 and get 60. Or 5 minus 2. Ugh. What am I doing here? So 5 minus 2 times 180, sorry. So it'd be 3 times 180, which is 540 degrees divided by 5. So We can't do anything with those to add them up to get a nice 360 vertex like we can in the first one there. Determine whether the given regular polygons can be used to form a tessellation. If so, draw the tessellation. So look at A and B, come up with their angle measures. Or do they go into 60 or 360? Can we make a tessellation out of these? And if you can, draw the tessellation. Give you a couple minutes, do those. All right, let's take a look at these. The first one is a hexagon. And if you take 6 minus 2 times 180, you get 720, which is, if we divide that by 6, we get 120 degrees at each angle, and 360 is divisible by 120. So because 360 is divisible by 120, we can have 3 of those angles in each corner. So it should look something like that. It ends up looking almost like a honeycomb or a beehive type of thing. So you can have 3 of those vertexes at every, or 3 of those angles, I should say, at every vertex. The next one, we have a square and a hexagon. So again, a hexagon is 120 degrees. A square is 90 degrees. So is there any combination where we can add 90 and 120 and get 360? In other words, 120 times X and 90 times Y. Is there anything that X and Y can do to get to be 360? And that's no, because, you know, if we have 120 and 190, that's 210. If we have 2 120s and a 90, that's 330, sorry. And if you have 3 120s, you can't have any 90s and you got to have 1. If you have 1 120 and 2 90s, that's 300. 3 90s would be 390 and so on and so forth. So no, there's no combination that makes that available for a tessellation. And that's all I have for today for the tessellations. So I'd like you guys to do the assignment that is on the board there. Work on those problems for Monday. And Monday I'll be back and we'll work on 9.7 on Monday.